Welcome to Math 31. This is the second part of the lesson on the quotient rule. Just going to look at a few examples of some variations and things of questions that you run into using, in most cases at least, the quotient rule. So for this, we want to determine the x-coordinates, only the x-coordinates, where the tangent line to this function is horizontal. Now this would mean that the derivative will be equal to 0. So really this is what's being asked. Where is dy dx equal to 0? Because that's where the tangent line will be horizontal. So this would really represent a turning point in the curve. So it's got big implications down the road when we start getting into applications. For now, we can treat it as simply as this. Now we're going to have to differentiate this. It shouldn't be too bad. U is equal to 2x squared. So u prime is equal to 4x. And then v is equal to x minus 4. So v prime is equal to 1. So y prime, as always, is equal to u prime v minus u v prime over v squared. So y prime is equal to 4x times x minus 4 minus 2x squared times v prime, which is 1. And this is all over top of v squared, which is x minus 4 squared. So y prime is equal to 4x squared minus 16x minus 2x squared, all over x minus 4 squared. So we could write this now as dy dx is equal to 2x squared minus 16x over x minus 4 squared. Now I should also note that the original function x cannot be equal to 4. It doesn't affect us much now, but we should be aware of that always. Now where this is equal to 0 brings us to this point. So we set the derivative to 0 and then we solve it. And it presents us with a couple choices. Now many of you correctly will multiply both sides by x minus 4 squared and then solve the resulting equation. Fine, and it's correct. But what I'm going to encourage you to do, if this function is equal to 0, really we're concerned with where is the numerator equal to 0. Because the denominator cannot be equal to 0. The numerator, though, can be. And this 0 on top will make the expression equal to 0. So you can bypass all the cross multiplication and multiplying both sides by x minus 4 squared and go right to this stage where 0 is equal to 2x squared minus 16x. Solve this the way you might normally solve it. Factor out a 2x, take a common factor out, leaving you with x minus 8. And then when you set that to 0, 2x is equal to 0, x minus 8 is equal to 0, and x is equal to 0, x is equal to 8. Now both of those numbers are not on the restricted list. They're within the domain of the function. So therefore, there's our answer. X is equal to 0, x is equal to 8. All we wanted was the x-coordinates. The question could just as easily have said find the points, which is what this one does say. Determine the points in the graph of this probably should be in this position. Graph of y equal 3x over x minus 4, where the slope of the tangent line is negative 3 over 5 as exact values. And just for a break, I'm going to change this to x coordinates. You'll see that's not a big deal, but it will make our lives a little bit easier. And getting the y coordinates is not difficult. It's just a bit time consuming. So this one works the same way basically, except we want to find out where is it equal to negative 3 over 5. So we can start by getting the derivative. U is equal to 3x, so u prime is equal to 3. V is equal to x minus 4, so v prime is equal to 1. So this one actually differentiates quite well, quite easily. Y prime is, as always, u prime v minus u v prime over v squared. So y prime would be equal to 3 times x minus 4 minus 3x times 1, so that's good news, all over v squared, which is x minus 4 squared. Y prime is equal to 3x minus 12 minus 3x over x minus 4 to the 2. Now interestingly, the numerator will lose its variable, and you're left with negative 12 over x minus 4 squared. This is not a big deal, though. If we were setting it equal to 0, it would matter, but we're not. We're actually setting it to negative 3 over 5. So negative 3 over 5 is equal to negative 12 over x minus 4 squared. And here you can multiply both sides by the least common denominator, 5 bracket x minus 4 squared. That's how most people are trained, or cheat by using the forbidden act of cross multiplication, which is what I'm going to do. Negative 3 times x minus 4 squared is equal to negative 60. And then when you divide by negative 3, you'll get x minus 4 squared is equal to 20. Take the square root, plus or minus, of both sides, and you'll get x minus 4 is equal to plus or minus root 20. Now root 20 is going to break into plus or minus 2 root 5, so root 4 times root 5. So x is equal to plus or minus 2 root 5 plus 4. And those are the x coordinates. Ask for them as exact values. They would be quite easy to decimalize if you needed to. Now the next question is actually an application. So a motorboat coasts towards a dock with its engine off. Its distance in meters from the dock t seconds after the engine cut is given by that equation, with the given domain between t between 0 and 6 inclusive. If you take a look at the function, you know that t cannot be equal to negative 3, but you'll also know that that doesn't really matter because negative 3 is outside the domain. So everything's looking fine. What's going to happen with applications, particularly when we focus on them in the next unit, is making sense of the equation or the question with respect to the equation, because typically you'll have 2, sometimes 3 equations to work with, and you need to always be aware of which one you use for what purposes. So for example, how far is the boat from the dock initially? Now if you take a look at the information carefully, you'll know that what you're trying to do is find out what the position is at t is equal to 0. So we find s at 0. So we're not even using a derivative. We just plug in 0 into this function. So s at 0 is equal to 10 times 6 minus 0 over 3 plus 0. And s at 0 is therefore equal to 20 meters. And I'll say from the dock. So nothing to it, as long as you use the right equation. Now the next question, though, says what is the boat's speed when it bumps into the deck? And this will require you to do a little bit more. So what we ultimately want is v at some time value when it's actually hitting the dock. Now many of you will say, well, based on the original question, t equals 6 is when we come to a stop. So happens you're right. But a safer way to do it, however, is to recognize that if we can find the time when s is equal to 0, we actually would be getting the time value when the distance is 0. That's what we want. So we go back to the original function and we get 0 is equal to 10 times 6 minus t all over top of 3 plus t. And as we did with the previous question or a couple questions ago, I just worry about the numerator because that's where it's equal to 0. So 10 times 6 minus t. Divide by 10 and you'll get 0 is equal to 6 minus t. Solve for t and t is equal to 6. So that is in fact when it comes to a stop. So if we find v at 6, then we're in business. Now the other thing is we don't have a velocity or speed function, so we need to be aware that v is equal to ds dt, the derivative of the position function. So given that s is equal to 10 times 6 minus t over top of 3 plus t, to differentiate this, I would advise you to take that numerator and distribute the 10 in so that we don't have a product up top. So we just have two terms. So I'll do the usual thing. I'll make u is equal to 60 minus 10t. So therefore u prime is equal to negative 10. And I'll make v is equal to 3 plus t. So v prime is equal to 1. So y prime is equal to u prime, negative 10, times v, which is 3 plus t, minus u times v prime, which is 1 times 60 minus 10t. And this is all over top of v squared. So 3 plus t squared. So y prime is equal to negative 30 minus 10t minus 60 plus 10t. This is all over top of 3 plus t squared. I have to go backwards in this case. So y prime is equal to, the t's cancel, we get negative 90 all over 3 plus t squared. So what this means is v is equal to ds dt, which is equal to negative 90 over 3 plus t squared. And to get v at 6, we just substitute the 6 into that function. So we get negative 90 over 3 plus 6 squared. And that gives us 1.1 meters per second. Negative 1.1. Now people ask about the negative, but v is actually equal to the change in d or change in position with respect to time. So if its position is getting smaller, which it is, because you're getting closer to the dock, we would then expect the rate of change of position with respect to time to be a negative value. The delta d, if you like, I'm just going to throw this in here, v is equal to delta d over delta t. Your change in d is going to be negative because it's starting at a bigger number, going to a smaller number, etc. So it doesn't really matter because speed is not a vector if you think back to your physics. So you can just say the speed is 1.1 meters per second. Now that's the instant that it comes into contact with the dock. Obviously it would either rebound or change its speed to 0. But just before it strikes, so when the distance has shrunk to nothing, then you get 1.1. So that'll take care of the quotient rule. The next lesson will be on the chain rule, where things start to get interesting. Thank you for your time.